problems which is directly from the hospitals, where they definitely need the numerical PDEs to solve and predict the cancer treatment, whether it will be working or not. They introduce some heat in that liver where the tumor is located, and that will be killed. Now, for this one, we need a heat equation, which is called as a bioheat equation. Basically, that bioheat equation, what does it do is that, for example, if we are doing exercise, our body internally produces some amount of heat. That is the reason we are getting the sweat and all. A similar kind of equations we got to solve, which is called bioheat equation, okay, which is introduced in 1950, earlier than that. But nowadays, it is getting popular because of that, and the biomechanics people are also using that. They introduce some heat in that liver where the tumor is located, and that will be killed. Now, for this one, we need a heat equation, which is called as a bioheat equation. Basically, that bioheat equation, what does it do is that, for example, if we are doing exercise, our body internally produces some amount of heat. That is the reason we are getting the sweat and all. A similar kind of equations we got to solve, which is called bioheat equation, okay, which is introduced in 1950, earlier than that. But nowadays, it is getting popular because of that, and the biomechanics people are also using that. Delhi is having 0 degree and Kathmandu is having 0 degree, then in between states mostly it may, if there is very nearby, that is also going to have either between 0 or it will be negative or positive, it is going to be that. But it is not going to have 50 degree if that city is very near to Kathmandu or if it is near to Delhi. There was a dam breaken in the Himalayan, then how that flow will affect it. Okay, that's an environmental science. Now these are all interconnected. Like if you take a climate change, because of that there is a flow is going to come, and that is going to devastate the entire country or some of the places. Then again we go to see that. So these are all the things the people are studying and using the PDEs, and they try to predict whether they can see that. For example, tsunami they are able to predict earlier, but still that earthquake prediction still is
pending.
Still a challenging task. So the supercomputer can do that, but the challenge is that once again you need a lot of power for that. Supercomputers requires megawatt powers, for one calculation it may require at least some $200. So for 10 days prediction you require, if I am just running on a normal PCs, it will require like millions of dollars. So that is not possible. So in that case, like the GPU computing and the advanced quantum computing and all, they are investing, and if they can get that calculation in fraction of seconds, okay, 10 days prediction, suppose I can get it in a minute, then
by quantum computing,
GPU computing. So these are the advanced technology they are using it. If they can predict it, then that will be the best thing for the future.
Welcome to Panchatcharam Mariappan, sir, to Nepal.
Thank you.
So how are you experiencing Nepal, sir?
Yeah, it's a nice country, nice weather, and I like the food and the architecture, cultures. It's very nice.
And how was your program?
Yeah, it was very interesting, and we had very good participants, and they were mostly interacting with me regarding the Python and some of the mathematics stuffs with me.
Okay, sir. So today we are especially talking about the numerical partial differential equation and its application in our daily lives. Okay, and its importance for the technological advancement and for the development of the nation, and its uses to the normal and ordinary people too. Okay, sir. So firstly, I would like to ask one question, sir. Could you introduce yourself and describe your expertise in the mathematics, particularly in the context of partial differential equation?
Sure. So basically, I did my mathematics from the remote place in India, which is called Sivakasi, which is very well known for the crackers. And I did my master's there and bachelor's as well. Then I moved to PhD in IIT Madras, which is in Chennai. And part of that, I got a Ph.D. from DAAD, which is a German academic exchange, where they provided some funding. I moved to Germany for a sandwich PhD program. And there I got more exposure about the numerical PDEs. So then later onwards, I become an expert in numerical PDEs. So I have more knowledge on the numerical PDEs then onwards, and I after that I worked as a industry. In the industry, we applied that numerical PDEs to solve some of the cancer treatment problems, and we developed some software tools which is available to predict the cancer treatments to the hospitals in Europe. Then later I moved to academia. Currently I'm working as associate professor. So I joined as an assistant professor in 2018 in IIT Tirupati, the Department of Mathematics and Statistics. So Then I become a head of the department in Department of Mathematics and Statistics, and just recently I was relieved from that, and that tenure got over. And also I'm serving as a computer center advisors in IIT Tirupati, and further I'm also the channel coordinator. Like in India, we have a national channels are there, which is mostly telecasting the mathematics to public through the direct to home, which is called Swayamprabha. So for that also I'm one of the national coordinator in that, our channel coordinator, where we are telecasting mathematics. So our idea is to broadcast not only in English, but we are telecasting in local languages like Tamil, Telugu, Nepali. So we are identifying people who can talk. And apart from that, I am also a DAAD Research Ambassador. So 2015, German has given that Research Ambassador award as well to me. And this is a brief about me. And the regarding numerical PDEs, as I have already explained, I have completely involved in that problems, which is directly from the hospitals, where they definitely need that numerical PDEs to solve and predict the cancer treatment, whether it will be working or not.
So, okay, what are the partial differential equations, right?
Yeah.
And how numerical methods work with it?
Okay. See, for example, I can give two examples, which is straight from my research. One is on that cancer treatment.
Yeah.
For example, in the cancer treatment, one of the common cancer treatment is the liver cancer is the one of the common. So the problem here is that the doctors, not experienced doctors, are there. So in that case, when they put that treatment, so the best treatment for that is like they have to completely transplant the liver, but that may not be possible. So the second choice is they got to go for surgery. That is also complicated, so it is not doable. So then what they do is that they introduce some heat in that liver where the tumor is located, and that will be killed. Now for this one, we need a heat equation, which is called as a bioheat equation. Basically, that bioheat equation, what does it do is that, for example, if we are doing exercise, our body internally produces some amount of heat. That is the reason we are getting the sweat and all. A similar kind of equations we got to solve, which is called bioheat equation, okay, which is introduced in 1950, earlier than that. But nowadays it is getting popular because of that, and the biomechanics people are also using that. Now for that equation, what we can do is that using that equation, whether we can say whether they have killed enough number of cancer cells or not. So that we got to identify that. So for which what we did is we solved numerically, because those kind of equations are like completely not easy to solve it. And also like we need to solve it in a fraction of seconds, because the treatment itself goes for 20 minutes and it is not possible to solve it quickly. So what we did is we solved it numerically, and also we have used a latest technology called GPU computing, which is if you have remember NVIDIA company, which is now the popular company, and they have the highest billionaires. Okay, so they are
the computer machines like graphics card.
Yes. Yeah. So they are the popular one right now, and they are the top company right now. They just bypassed the Google, and then they are the top company. So that technology we have adopted, and we were able to predict that simulation. I mean, the prediction of whether the cells will be died or not, etc., within 2 minutes. So that is the advantage of the numerical, so that the doctors can change their idea whether they have to go for this protocol or the other protocol, etc., that they take it. So that is one example. The second example, again related to the timing only. For example, if you take suppose I want to see like what is the weather in Nepal today. Okay.
Yeah.
So that requires a lot of numerical PDEs. Means PDEs are first of all required.
Yeah.
But again, that PDEs you cannot solve it analytically because it is not possible to solve it. So in that case, we need the numerical PDE. So that they called as a numerical weather prediction. So in short, they called as NWP. So that many models are there. So they introduce some heat in that liver where the tumor is located, and that will be killed. Now for this one, we need a heat equation, which is called as a bioheat equation. Basically, that bioheat equation, what does it do is that, for example, if we are doing exercise, our body internally produces some amount of heat. That is the reason we are getting the sweat and all. A similar kind of equations we got to solve, which is called bioheat equation, okay, which is introduced in 1950, earlier than that. But nowadays it is getting popular because of that, and the biomechanics people are also using that. They introduce some heat in that liver where the tumor is located, and that will be killed. Now, for this one, we need a heat equation, which is called as a bioheat equation. Basically, that
yes,
bioheat
exactly.
equation, what does it do is that, for example, if we are doing exercise, our body internally produces some amount of heat. That is the reason we are getting the sweat and all. A similar kind of equations we got to solve, which is called bioheat equation, okay, which is introduced in 1950, earlier than that. But nowadays it is getting popular because of that, and the biomechanics people are also using that technology.
So that's nice, sir. Okay. So what are the key mathematical principles, sir, for solving that partial differential equation numerically?
Okay, so if we come to the numerical PDEs, so basically what we have is that we have two things to be taught, said in that. One is about the domain. Okay, for example, if I take the numerical weather prediction, our Earth and the atmosphere is the domain for me. And the governing equation, which is called the partial differential equation, it will be Navier-Stokes equations or other differential equations will come into the picture because the flus and other things are involved over there. Now we got to discretize both the things because these two are continuum things. Domain is also a continuum and equation is also a continuum thing. So these two continuum things, you cannot solve it very quickly. Okay, so for that purpose, what we have is that we collect the weather data from many different places. So every altitude and every kilometers, they take it and they put some weather stations and they collect the information. Now what we have is, that means we discretize the Earth into small cubes or small discrete points.
Discrete parts, yes.
So for that discrete points, okay, we need to know the information at each discrete points, and then we put that information from the data science and data, etc., and then they put it in that numerical solvers or numerical PDE. Now this PDEs, again, you cannot solve it easily. So what we got to do is that we got to use the Taylor series approximations
exactly.
or other approximations like weak formulation, etc., and then they try to make it as a again a discretized linear systems. This will become like a larger linear system. It will contains like millions of matrices. The matrix may contains like millions of elements will be there, or sometimes billion elements will be there, and those again they go to solve it. Now they know the information at the discrete points. Now based on this, they just interpolate. Suppose if I know the information about Delhi and Kathmandu, or let's say Pokhara, and in between cities, how do we calculate that? Because they don't have weather station. So they use this information and numerically predict it, interpolate it, and then say like this may be the temperatures around that. Because if Delhi is having 0 degree and Kathmandu is having 0 degree, then in between states mostly it may, if there is very nearby, that is also going to have either between 0 or it will be negative or positivity is going to be there. But it is not going to have 50 degree if that city is very near to Kathmandu or if it is near to Delhi. So that like that way they just predict it using the numerical interpolation, and then they do that.
Okay, what are the methods and approaches, sir? Just like the finite element and spectral methods or finite difference methods?
Okay, so basically, the PDEs can be classified into three types. One is called elliptic, parabolic, and hyperbolic. For example, if we take the heat equation, those kind of equations, we can solve it either using finite difference method or you can use the finite element method. So depending on the structure of the problem, means the domain of the problem, they just choose like which method can be easily done. For example, if we have a liver geometry, in that case, I cannot use the finite difference method easily because the discretization will miss out many points because the topological figure will be different in this case. So in that case, we go for the finite element method where the elements will be like small triangles I can fill. The space filling curve is very important. So if those space filling curves can give that triangles can be or tetrahedron can be given, so in that case, we go for finite element method. But if our geometry is very simple like square or some rectangles, in that case, I don't need to go for very complicated things. I can simply go for finite difference method for the domain discretization. Now once we come to that again for that equation discretization, again there are advantages and disadvantages. So finite difference method, straight away it uses the Taylor series approximation and they call it as a strong form. Whereas in the finite element method, they call it as a weak form because they will be doing the integration. Instead of solving that as a differential equation, they will put the integration and then they will use the integration pi parts. So once the integration pi parts is there, then what will happen is that the second order differential equation will become like a first order differential equation because one, they will throw it out of the derivative from the integration. So that means like you require a second order solution, but in fact you are getting a first order solution. So that means it's called a weak solution. So it has some advantages and disadvantages in both sides. It is there. Similarly, there are like methods like finite volume method, generalized finite difference method, spectral method, smooth particle hydrodynamics, especially in astrophysics and all. It's a free flow. So in that case, they cannot use these kind of method because the boundary is not fixed there.
All methods have their own importance.
Yes. Its own importance. Like mostly that smooth particle hydrodynamics and all, they invented for that astrophysics, because there it is completely open. The astronomy is completely open, so they can space. So there is no boundary for that. They cannot find that. So in case of finite element, finite difference method, we can confine to some certain region and then we can apply that. But in this case, we don't know, like when there is a big bang or where there is a cluster is just blasting, we don't know where that particles will go. Okay, so in that case, these methods cannot confine. So then they go for the smooth particle method, hydrodynamics method, where they can throw the particles anywhere. And apart from that, there are methods like lattice-Boltzmann method, especially in terms of chemical engineering and other things. It is there.
Okay, so what are the difference between that analytical versus numerical solutions methods?
Okay, so what we want is actually we want our analytical solutions only always, because if we have analytical solution, we don't need to worry about what is going to happen, and also we can analyze that better whether it is going to fall or it is not going to fall, etc. For example, one of the still unsolved problem is the regularity for the Navier-Stokes equation. It is still a $1 million problem which nobody has solved so far. So the problem is that existence and uniqueness. So if it is analytical solution, means like we have already the existence is there and we have the uniqueness is there, then we can say like if I give this input, I'm going to get the output. So that is not possible. That is possible in the analytical solution. That has a big advantage. But in reality, what is happening is that many of the phenomena we cannot predict, we cannot solve it analytically. So in that case, what we are trying to do is that whether we can at least get the approximate solution. So in the approximate solution, there are different ways they do. Like they can just take that partial differential equation is highly non-linear, and they try to make it like a linearization. And they say try to say whether we can get that flow or whether we can get that turbulence, etc. They try to do that. That's one way. Then again, they go for that linearized equation. They try to calculate the analytical solution in mechanical engineering and computational fluid dynamics, etc. Whereas in some cases even that may not be helpful. So what we need to go for is we need to solve the differential equation and we apply that discretization in the numerical way, and then we try to see like whether we can get solutions at the discrete points, at least based on that we can do the interpolation. So that therefore like we get some for very unknown problem, very complicated problems. For example, I cannot simulate aircraft where I want to study like what is the strength of the aircraft, whether if there is a fire or something, whether the aircraft can sustain and all. It's an experimental thing which they cannot do it. So in that case, again, we need to go for the numerical differential equations, etc. That gives a lot of benefits.
Okay, so we just talked about some foundations of the numerical partial differential equations. Mm-hmm. Okay, so and another part we go to the real life applications. So can you please describe its importance of partial differential equations in the field of the science, just like the environmental science, physics, engineering, medical science, etc.
Yeah. So medical science, I have already explained, like cancer treatment where we have already applied. Yeah. And I have explained one, and there are plenty of others are there. Like in some of the models, we need to talk about the flood flow also, because that is also going to have an important thing. And now that stenosis and other things, they put it, and that becomes like a nano fluidics things. So again, they cover that using the partial differential equation and then try to see like whether it's a flood flow. The flow is flow. Either it's a flood flow or river flow or the flow in that around that air flow around that aircraft,
or blood vessel flow also. Yes.
So flow is a flow. So we have similar kind of equations. Maybe the parameters may change, or some of the additional source terms, etc. will come into the picture. So the flow is flow. So either it's a medical field or environmental science, because the flow is again there in the environmental science. Suppose there is a disaster is there. Suppose all of a sudden there was a dam break in the Himalayan. Then how that flow will affect it. Okay, that's an environmental science. Now
Yeah,
these are all
yeah, yeah.
interconnected. Like if you take a climate change, because of that there is a flow is going to come, and that is going to devastate the entire country or some of the places. Then again we go to see that. So these are all the things the people are studying and using the PDEs, and they try to predict whether they can see that. Recently, like I have been part of some of the landslides where that also they're trying to predict, like IIT Mendi and NIT Mizoram. There are some groups working on like how to predict that landslide, and they can see like whether they can create an app or software where they can see like when there is a landslide whether we need to evacuate the people or something.
Yeah, yeah.
And another thing like earthquake, okay,
Yeah.
which is very common in Nepal.
Yeah, yeah.
So that also, if we can predict it very early and we
Early.
can evacuate the people, that will be helpful. So that is
So
one of
is
the
earthquake prediction is possible through this numerical partial differential
people
equation?
are working on that, but still there is not 100% success on that.
Yeah, yeah.
Still they are doing it. For example, tsunami they are able to predict
Yeah, yeah,
earlier,
yeah,
but
yeah,
still
good.
that earthquake prediction still is
It's
is
pending.
yeah, it's still a
pending.
challenging task.
Okay, so and what's about the climate change?
So climate change, there are plenty of models are there, and different combinations of people are working, and still like there are like plenty of things are unsolved in that as well.
Okay, so we have already discussed about the medical things. Okay,
Mhm.
it's not more to explain.
Mhm.
Okay, so let's go to the topic about the computational challenges. Okay, so what are the main computational challenges for that solving the numerical PDs, and how it is being addressed, sir?
Okay, so the first thing is that the computational challenge is that when the geometry of the problem is complicated, first of all, discretization is going to be a challenging thing. Okay,
Yeah.
because
Yeah.
we don't know where that singularity is going to be there, etc. That is one of the biggest challenge in that. The second thing is that the computational power, because for example, if I say like I have to predict the 10 days weather.
Yeah.
So what I got to do is that I got to discretize the equation, means the domain itself. I got to discretize into small squares and all. So that will give almost like 10 power 6 discrete points it will give.
10 to
Once
the
I-
power 6.
Yeah.
Yeah.
And if I put that in the
Yeah.
PDEs and then convert it into a system of linear equation, it will become like 10 power 12 systems.
Yeah.
Okay.
Yeah.
So with the computers, like suppose you have a laptop.
Can computers solve this type of the solutions?
Normal computers cannot do that. That's
Yeah,
why we need a supercomputer.
Supercomputer, right?
So the supercomputer can do that, but the challenge is that once again you need a lot of power for that. Supercomputers requires megawatt powers,
Megawatt
and
power. Yeah.
for one calculation it may require at least some $200.
Yeah.
So for 10 days prediction you require, if I am just running on a normal PCs, it will require like millions of dollars.
Millions of dollars. Sure.
So that
sure.
is not possible. So in that
Yeah.
case, like the GPU computing and the advanced quantum computing and all, they are
Yeah.
investing. And if they can get that calculation in fraction of seconds, okay, 10
Yeah.
days prediction, suppose I can get it in a minute, then
by
that
quantum computing,
GPU
right?
computing. So these are the advanced technology they are using it. If they can predict it, then that will be the best thing for the future. And still, like some of the problems like the climate change and other things are still like very
Complicated,
and
yeah.
they need to solve plenty of equations. Though
Sure.
because everything is interconnected. It's a kind of chaos theory.
Sure,
One
sure.
small thing affected will be affecting the entire globe.
Entire globe, yeah.
So those things they need to solve many things. So again, we require a very superpower computer.
Superpower computer.
Yeah.
Okay,
And not only that, like we are talking mostly the climate change with respect to what is happening in the earth. But some of the astrophysics also going to come into the picture in this. Like suppose some other planet is affected by the sun,
Yeah.
and some what is that meteorites? Okay, they are going to
Meteorites,
hit
yeah,
it. Okay,
yeah.
then what will having the impact? So those and all we are not studying because that is also
Yeah,
having
exactly.
some impact. So that and all not coming to the picture because many of the parameters we are ignoring.
Yeah.
So in that case, definitely this computationally it's not solvable
Okay.
by our lifetime.
That's okay.
Yeah.
Sure. I think so many things have to do in the field of this computation, right,
Yeah,
sir?
yeah.
It's just the beginning
Yeah.
throughout the globe.
Yes.
Okay. So, and another one is the questions to accuracy and stability.
Mhm.
That is, how do mathematics ensure the accuracy and stability of numerical solutions to partial differential equations?
Okay. So basically, whenever they develop a numerical methods for the PD, what they try to say is that they take always a benchmark problem,
Yeah.
and then they try to see whether that has some accuracy or not. Okay.
Yeah.
So if that accuracy is there, then they will just go for applying that to some complicated problems. So they study the stability and everything in a benchmark problem we call it as like simple toy problem which the academia they used to take it. But the real things which they go to do is that, for example, as I have already mentioned in that cancer treatment one, which we have developed a software and which we have tested on hundreds of patients, and we checked whether that is numerically stable and whether they gives the accuracy, because we got to validate that, because the PDEs or numerical PDEs, we are just trying to model it in a paper, okay, and try to simulate it in the computer. But once we apply to the reality, it may be failure also. So in that case, definitely there is a validation is important. So mostly we try to validate whether it is giving the correct answers or not. If it gives the correct answers, okay, then we just say like, okay, this is a better method compared to the other one that we say that. So then for accuracy, again, we need more mathematical things, like we apply the norms between the two functions, and the stability, again you need to see like whether small changes in the input, whether it is going to affect the larger output. Okay, small changes would not affect the larger things, so those things we just check it in the stability.
Okay, sir, another thing is, sir, what is the role of that? You have already said about the computing, that supercomputer is needed, but what is the roles of that high computing, high performance computing in advancing that PD's solution?
Okay, so in this case, actually, nowadays the machine learning is also coming to the picture, because nowadays what is trending is that they try to take the PDEs or ODEs and then they try to solve that using the machine learning. Means they train the model in such a way that can do that. So now, although the computational powers are required for this machine learning, now what they try to do is that they try to simulate some toy problems, and then they train that model in such a way that whether they can use it for the complicated things that they are trying to do. So because of this artificial intelligence and machine learning, that is also going to have a lot of impact on this one. And again, like machine learning, once again you require a lot of computational. So we have both benefits. So PD is also helping the HPC to solve some of the heat equation, whether we can optimize some of the things, and from that they try to do. And HPC is helping again to solve the PDEs, etc. So both ways it is advancing.
Yeah. So another is the future directions, and what are the some emerging trends and future directions in the research and applications of the PD's solution and numerical PDs?
Okay. So there are plenty of, in the medical science, there are plenty of applications are there, especially in the biomechanics, because many people didn't touch many of the applications of that biomechanics with respect to the PDs. That is one application. And second thing, already we discussed the climate change, okay, which we are just taking only few parts of that and then we are trying to solve it, but we are not interconnecting many of the things. For example, if there is a war happening in Israel, or if it is in the Ukraine. That will also affect our climate change. But that is also, that and all we are not taking into the account properly. So those things and all is a future thing. So
that are the parameters. We also need to take a parameters. One parameter. So okay.
So those also has to be incorporated so that the PD will become complicated and it will be more like modeling is also required, and then we got to solve that also. Complications will be there. So all these interconnected things will be there. And not only that, like suppose there is a change in the climate and that will affect our body as well. So that also, like again the biomechanics is going to play the role. So all these things are interconnected. So definitely we need a lot more efforts are required in terms of the PDEs and numerical PDEs.
Okay, so sir, and what skills and the knowledge are essential for students aspiring work in the field of the numerical PDEs and related areas? What knowledge should students have if they want to grow?
Okay, so the minimum thing which you require is at least they need to have a basic mathematics. Okay, because nowadays the trend, if we see in India, is that like those who have mathematics and computing is getting more paid than the computer science students. Okay, that's the trend. So mathematics, because that is one of the fundamental blocks for many of the engineering sciences as well as the machine learning and data science. So maths and statistics is the key playing role. So now the students who wants to know the numerical PDEs, first of all, they need to know about two things. They have to put two hands on that. One is they should be strong in the mathematics. Another is they should be strong on the computing. Okay. So these two, if they have the strong background, definitely they can do that. So at least they should know like how to write a program in Python. Okay,
The
which is very
Python.
simple thing. So
Yeah.
at least they should know very simple things and the Python. Then they can learn. They can do the coding and other things, and then they can train the machine learning also, because most of the machine learning packages are available in Python. So they can
Yeah.
do that, either TensorFlow or Keras or Scikit-learn. All these things are in Python. So that they can use it for training the PDEs. Okay, at least if they have that knowledge, they can do that. The second thing is that they have to know the PDEs. Okay, what is the PDE? What does it physically represent? So if they got the PDEs output from the machine learning, whether it is making sense or not, that they should be able to judge it.
Exactly.
So that skills also they require. Okay, because PDE, if I give a PDE, ChatGPT or Gemini or Copilot can give the answers to me. Whether that is giving a correct answer or not, how do you judge that?
Yeah.
So for that you need that intuition first of all, and then you go to say whether it is making sense or not, that you go to, because
sure.
we cannot believe on the AI and ML all the times whether it is giving correct or
Yeah,
not.
sure,
Okay?
sure.
So in that case, they need that skill as well. The analytical skill is required for
analytical and thinking power is also
yeah.
required. Okay, sure.
Yeah.
So and at last we are on the behalf of the conclusion. Okay, so could you summarize the importance of numerical PDs in the modern science and technology and their potential impact on the future developments?
Sure. So, for example, if I'm just talking in this YouTube channel or in the media, so I have some wave equation is going to be there, because that wave is converted into this channel and we have that one.
Yeah.
So all these things, because wave equation, if I say, it's again a PDE.
PDE,
okay, so,
exactly.
So those PDE, we are just again like there is a noise killing, everything we are just incorporating that. So all these things are very important. Okay, so again like there is a PDEs are involved in many of the machine learning models. But once I solve that, when I take a machine learning model, okay, what is it going to do is that it is trying to fit the models in the proper way. Now what it is supposed to do is that it has to calculate the optimized thing. How do you calculate the optimized thing? Because you need the calculus. What is calculus? In calculus, again you require the partial differential equation where you take the derivative with respect to partial derivative, you take it, and then you try to solve that. So wherever you land it, again you may be ending up with this numerical PDEs, whether you go for the machine learning field or you go for that climate change or cancer treatment, whatever it is, you will be landing it in some of the numerical PDEs, and then those things definitely you need to solve it using that numerical PDEs, because you cannot solve it analytically all the time. Some of the type problems you can solve it, but you cannot solve that. So therefore, most of the modern science, either it's a chemical engineering, mechanical engineering, or civil engineering, or aerospace engineering. So many places, this numerical PDEs are having application, and they are playing a vital role in
vital role.
Yeah.
Sure. And another last one is, so do you have any advice for the listeners interested in learning the more numerical PDEs or pursuing studies and career in this field? And how is the field in the world? Okay, so is this more beneficial to our students who learned these PDEs can earn more money also? Okay, so at last money also comes, right?
Yeah.
And how the students can make the career in this field? Okay, so what are the job opportunities?
Actually, industries are looking for most of the people who has the, first of all, the computing knowledge they require. Okay, so the numerical PDEs definitely it gives the computing knowledge, so you can learn that things, and then you can have that development of the logics, etc. That is going to come into the picture definitely. So therefore, the industry is going to hire you because you have the numerical things, so you learn the basics of the computing, so that is definitely required. And there are many industries like biomedical industry, aerospace industries, mechanical industries, so they are also interested on that. For example, I have some 2-3 examples I will give it, and then I will just tell you. So the company which I have worked is working on the aerospace and biomedical and other things which we are working. So they are paying a lot of amount for this one.
Yeah.
So either you have a knowledge about a lattice Boltzmann method or finite element method or finite volume method, that they are employing in their model, and then they try to do that. And banking sector, if you take it, again they need to solve that Black-Scholes equation, which is again the finance problem. Again they do the same kind of things. They try to solve that finance predictions, stochastic PDEs they call it as.
Sure.
That requires the finance market, etc. Again they need the numerical PDE persons, whether they can solve it or not, whether they can fit it properly or not. All these things they require. Again, there is a lot of things where they get a lot of money from that. And the third thing or final thing which I can say is that, like if you go to the academia, okay, so there are also plenty of jobs opening for numerical things, because the machine learning, many academia is looking for people who can do that machine learning and that thing. So again, because you know that numerical things where you can apply that for the PDEs, etc. Again, they are looking for people who has the knowledge on not only numerical PDEs, but of course you have some basic knowledge about machine learning, then in academia also there are plenty of things. But in industry, they are paying a lot. But if you compare the academia, always they pay less, at least in India and some of these countries. But some of the European countries, if you have industrial mathematics or numerical PDEs, they pay a lot.
Okay, thank you so much for coming to our podcast Digital Soch. Hope our audience will enjoy the podcast. Thank you so much, sir.
Thank you. Thank you
so
for
much,
inviting.
sir. Okay, sure. Thank you so much, sir.